All right, probability of dependent events. Pretty similar to the same formula as the probability of an independent event, except for this second part. It has a weird symbol in it. So the probability of A and B happening, if they are dependent events, is equal to the probability of A happening, and then it has this weird probability of B with a line and an A. What that means is the probability that B happens if A has already happened. So you don't look at all of the outcomes. You only look at the ones with A have already happening. All right, so let's look at an example. Here's a spinner question, and I think this is a good one to show what it is that we're calculating. So as part of a board game, you need to spin a spinner. It's divided into equal parts. Find the probability that you get a 5 on the first spin and a number greater than 3. So the probability of getting a 5 and then a number greater than 3. Well, I've already made the sample space for you. So let's just look for the probability of 5 happening first, which are all of those, but then only numbers greater than 3 on the second spin, which gives me 5. So this becomes 5 out of 64. That's the probability of getting a 5 and getting a number greater than 3 the second time. If these were dependent, the probability of getting a 5 multiplied by the probability of getting a number greater than 3, if you've already gotten a 5, would also equal 5 out of 64. So let's look at the probability of getting a 5. Well, that's this entire list right here, which is 8 of them out of 64. The probability of getting a number greater than 3, given I've already gotten a 5, that means that even though this is bigger than 3 and this one has a number bigger than 3 and this one has the second number bigger than 3, they didn't get a 5 first. This one got a 5 first. This one got a 5 first. This one got a 5 first. This one did. This one did. So out of the 64, only 5 out of the 64 have got a number greater than 3, given that it already got a 5, right? So if this was dependent, when I multiplied this together, this becomes 1/8 times 5 over 64. That's supposed to somehow equal 5 over 64, which there's no way, because I've already got 5 over 64 and I'm multiplying it by another number. So that means this is not a dependent event. This is an independent event. All right, so let's look at example 4. A bag contains 20 $1 bills and 5 $100 bills. So I've got 20 ones and I've got 5 hundreds. All right, you randomly draw a bill from the bag and you set it aside. Then you randomly draw another bill from the bag. Find the probability that both A and B will occur. So this is asking, what's the probability that you get 100 and that you get 100 the second time? So here's where independent and dependent come in, because if I take the first event, the chances of getting a $100 bill, well, there's $500 bills out of 25 total bills. So that's the probability that event A is going to happen. If I don't put that $100 bill back, if I keep it, the second time I pick a bill, there's only $400 bills and there's only 24 total because I already took one of them out. So event A and event B are dependent because my first one changed my second one. So the probability of 100 and 100 is going to equal the probability of A times the probability of B given A. So, which I already found. The probability of A was 5 out of 25. The probability of B happening, if I already drew a $100 bill, that was 4 out of 24. So the total probability is going to be 20 out of 25 times 24 is what? 600. And 20 over 600 is going to be what? 20 goes into 600. What did I just do? I don't know how to make that go away. Oh, there we go. 20 goes into 600, what, 30 times? I think. So 1 out of 30 is the probability of getting a $100 bill on both of your draws. 1 out of 30. Okay, example 5. You randomly select 3 cards from a standard deck of 52. What's the probability that all 3 cards are heart when you replace each card and when you do not replace each card? Okay, so for those of you that don't know cards, 52 cards, there are 13 of each suit. So hearts, diamonds, spades, there's 13 of each, all right? So the probability of getting where'd my pen go? The probability of getting a heart and then a heart and then a heart, if I don't replace them and if I do. All right, so if I replace them, if I put the heart back, the chances of getting a heart the first time is 13 out of 52. The chances of getting a heart the second time, I put that heart back. So there's still 13 hearts and there's still 52 total cards. The third time, I also put the heart back. So there's still 13 hearts out of 52 total, which this simplifies to 1/4 times 1/4 times 1/4, which is going to be what? 1/64. Okay. Probability of getting a heart and then a heart and then a heart if I don't replace, if I don't put it back, is going to equal the first heart. There's 13 out of 52 chances. The second time, there's only 12 hearts left and there's only 51 cards left to draw from. The third time, there's only 11 cards left and there's only 11 hearts left and there's only 50 total cards to draw from. So I have to do 13 times 12 times 11 on the top and 52 times 51 times 50 on the bottom. Yikes. Let's do 13 over 52 multiplied by 12 over 51 multiplied by 11 over 50 is going to give me 11 out of 850. Yikes. Where'd my thing go? 11 out of 850 chances of getting a heart if you don't put it back. There's 1 out of 64 chances if you do put it back. There's only 11 out of 850 if you don't put it back. So the chances if you do put it back seem like they're a lot higher than if you don't put it back. So, all right. Couple examples. Do we need to do more? Yeah, really quick. If you're ready to start the homework, there it is at the bottom. I'm going to do a couple more with you just so you can kind of see what they are. What's the probability that you spin an even number and then an odd number? All right, so if I go back up to my list, the probability of getting an even and then the probability of getting an odd. Now, see, I've been doing probability for a long time. So there's different ways you can do this. One is to actually count them. Let's see. I've got to do evens first, which is all of those, all of those, all of those, all of those. But the second time I want an odd. So that one, that one, that one, that one, this 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 one. So that's what? 4 from each column. 1, 2, 3, 4 columns. 4 times 4, that's 16 out of 64, which is, yeah, that seems right, which is 1/4, okay? The other way that you could have done that is what's the probability of getting an even, and multiply that by the probability of getting an odd. Okay, probability of getting an even. Well, 1 through 8, half of them are evens. Probability of getting an odd, 1 through 8, half of them are odds. So 1/2 times 1/2 is 1/4. Either way gets you the same answer. Okay. In example 4, what's the probability that both bills are $1 bills? All right, well, the first time I pull a dollar bill, there are $21 bills out of 25 bills. The second time, there's not 20 anymore, there's only 19, and there's not 25, there's only 24, because I took a bill out and I kept it. So I have to do 20 over 25 times 19 over 24. Geez, who picked these numbers? 20 over 25 times 19 over 24. 19 out of 30. That's not too bad. So 19 out of 30 is the chance of getting 2 $1 bills. The chance of getting 2 $100 bills was a lot less, wasn't it? Yeah, it was only 1 out of 30. 19 out of 30 chances of getting 2 $1 bills, which means you have 10 out of 30 chances of getting one of each. Cool. In example 5, what's the probability that none of the cards are hearts? When you replace and when you don't. Okay, 52 cards. If none of them are hearts, that means I've got 39 that are not hearts out of 52. And I'm going to do that 3 times because each time I'm going to put it back, right? 39 out of 52, 39 out of 52, 39 out of 52. If I do put it back, I'm going to get 39 out of 50, or if I don't put it back, sorry. The first one I did put it back. That's why there was 39 each time. The second time, I'm not going to put the card back. So 39 out of 52 are not hearts. 38 out of 51 that are left are not hearts. And then 37 out of 50 that are left are not hearts. So when I multiply those all together, 39 out of 52 multiplied by 39 out of 52 multiplied by 39 out of 52. That gives me 27 out of 64, so 42%-ish. And then if I do 39 out of 52 multiplied by 38 out of 51 multiplied by 37 out of 50, then I get 41%. So it's not that much lower. 42%, and look at how close those percents are. So the chance of getting 3 hearts and the chance of not getting any hearts is really, really, really close to what we got before, right? Or I guess the chance whether you put it back or not is what's close, not the chance of getting them or not getting them. So, okay, 5.2. I want you to do 11 through 14 and then 17 through 20. I would stop the video, go do those problems, and then come back for the next part.